Let's understand how these interactive 3D world models that are like video game are built like GENIE 3. This is a video generation model where you can walk around, turn around, and it will properly generate the world you are walking in, you are turning around. MatrixGame is open source world model like this that's gonna generate video in this world where you can just interact with the world and the video will generate properly as if you are in the world. MatrixGame 2.0, an open source real-time and streaming interactive world model. You can actually run this, by the way, on your computer or you just rent a GPU. We will look through the code, but let's first look through the research paper. So it has these diverse scene types. You can walk around. The videos are very long. Then we have, let's see, this type. You can skip forward if you want to see the paper and code. I have chapters as well. Let me see this one. It looks cool. This is so interesting. I'm already thinking, how can we connect this to like other? So this is video diffusion model. I know that. And I want to see this. Actually, I want to see this one. This one looks cool. And imagine we also add audio here. Then we have GTA. They trained a lot on GTA footage and then also on Unreal Engine footage. So this is so cool. It works so well. Then they have some very long, 1 minute long videos. I want to be able to code this and train this from scratch if I'm being honest, but would probably require a lot of compute, but this company also released it in open source, so maybe it doesn't require so much compute. So they used 1x model. We'll see what this model is, probably text to video model, and they removed text part and added actions, part actions module. So now it predicts the next frames only from visual contents and corresponding actions. Let's quickly check the architecture. So we got video tokens, and then they are using some kind of self-attention. We'll see later what this means. And then cross-attention with a time step and image tokens. I guess image would be maybe for the future video generation. We'll see. And then we have mouse actions with MLP and mouse-driven self-attention, and there is a residual connection here, and then cross-attention with keyboard actions. So I guess mouse is for rotating and looking around, and keyboard is for moving. So it's similar to other. So this is diffusion transformer block. I've been coding these. If you go to my channel, I do this kind of research, but if you go down, you can see diffusion videos. So you can just search on my channel for diffusion videos. There are a bunch of diffusion, like diffusion LLM and other diffusion videos. Here, diffusion transformer, this is where this is the backbone of all of the diffusion models right now. OpenAI has really interesting paper from 3 years ago, but it's very interesting. They use this paper in making MatrixGame, video pre-training, learning to act by watching unlabeled online videos. This is the research paper. You need to download the whole repository and find it in assets. MatrixGame 2.0, an interactive world model, generates long videos on the fly via few-step autoregressive diffusion. I wonder what this few-step is. Our framework consists of 3 key components: a scalable data production pipeline for Unreal Engine and GTA 5 environments to effectively produce massive amounts, around 1,200 hours of interactive video data. I don't know how this is massive. This is not so massive. 1,200 hours. Feels like it's not so massive. So they generate data with GTA 5 and Unreal Engine. An action injection module that enables frame-level mouse and keyboard input as interactions. A few-step distillation based on the causal architecture for real-time streaming video generation. MatrixGame 2.0 can generate high-quality minute-level videos across diverse scenes at ultra-fast speed of 25 frames per second. We open-source our model weights and codebase to advance research in interactive world modeling. Let's go! Maybe we're gonna code this on my channel and train it maybe. I'm probably gonna do it. World models have gained significant attention due to their capability to understand real-world interactions and predict future states. We need to figure out how to merge text and video and world models and everything. And we need to figure out how to get better architecture than Transformer that doesn't have quadratic scaling. That's like for the next year. It's gonna be figured out, I think. By enabling intelligent agents to perceive their surroundings and respond to actions, these models reduce the cost of real-world trials and facilitate interactive simulation. So we will use this to train robots. Let's go. Consequently, world models show great promise in fields such as game engines, autonomous driving, and spatial intelligence. Recent advances in video generation models have shown remarkable progress in learning knowledge from large-scale real-world datasets, ranging from physical laws to interactive scenes. So recently, video models are learning the real-world knowledge, like physical laws. This demonstrates huge potential of video models to serve as world models. And this direct byte and pixel rendering is the future. So AI models are gonna take in bytes, not tokens, bytes, and then they're gonna output bytes, so pixels or whatever, the text bytes. The problem with that right now is quadratic scaling of the transformer. If you have one token, one part of image, it contains many bytes. So now your sequence length is gonna be a lot larger than just one token. You have now like 7-8 bytes. So the quadratic scaling of transformers. So we need to figure out better mechanism to solve the problem of quadratic scaling and to solve the problem of bytes as inputs to models. So two problems with one solution. And there are many research directions in the video generation models, but these interactive video models have been getting popular lately because they can be useful for training robotics, but they can also be for video games and movies, and it's very useful to have interactive video generation. Yo, we're gonna do this on my channel. Guys, let's go, subscribe, drop a like, drop a subscribe, bookmark my channel. We're gonna be coding and training all of these. Where long videos should be generated in real time in response to a continuous stream of user input. This is why Elon Musk said they are training their models on bytes. I'm not sure which models, probably these image or video generation models, but probably soon LLMs as well. And that's why we want to do the same. I was doing research. These 4 last videos, there's a playlist. Here it's all about bytes into LLMs, this one. Despite impressive progress in interactive video generation, existing models suffer from several significant challenges. Lack of large-scale, high-quality interactive video datasets with rich annotations for training, such as accurate actions and camera dynamics due to high cost and difficulty of collection. I guess you can generate this with Unreal Engine. Latency issues with bidirectional video diffusion models, where generating a single frame requires processing the entire video. This makes them unsuitable for real-time streaming applications where the model must adapt to dynamic user commands and produce frames on the fly. The quadratic scaling of compute, yes, and memory requirements with respect to frame length, along with the high number of denoising iterations, yes, you need like 100 denoising iterations maybe, or 1,000, makes long video generation computationally intensive and economically impractical. So latency issues. So lack of data and latency issues. Too long to generate. And then severe error accumulation in existing autoregressive video diffusion models. While these models generate the next frame based on previous frames, they often suffer from error accumulation during generation, leading to degraded video quality over time. So you get a bit of a blur, a bit of a mess in one part of the video, the mess and blur will just spread and grow. And They designed MatrixGame 2.0, a novel framework specifically designed to achieve both real-time performance and robust generalization across diverse scenarios. So they have video diffusion transformer with integrated action control modules, distilled into a causal few-step autoregressive model via self-forcing based techniques. They have efficient KV caching mechanism, achieving 25 FPS generation on a single H100 GPU while maintaining minute-long temporal consistency and precise action controllability, even in complex wild scenes beyond the training distribution. That's good. We need to understand how this happens, why this happens, because this holds an answer in how we can unify these architectures into one. So they have Unreal Engine and GTA 5, and they developed some automated ways to move around and then to record and capture camera movements, inputs, so everything is automated. So this solves the problem of data and very precise annotations. And I think 1,200 something hours is not too much at all. I think companies will generate millions of hours. We can take a look from these screenshots. All of these, I suppose they are videos. They all look nice. Here, this one. This is GTA. What is this? And this is all Unreal Engine. And then Minecraft. This is easier to understand. Base model, and then foundation model supervised fine-tuning with action modules. Now, do they have this already pre-trained? Do they use their own? And when they say base model and then foundation model, so are they supervised fine-tuning this base model? So we'll see later. And then model distillation, I'm guessing this is to make the model smaller and faster. But we can understand this one easier. Input image, and this goes through video and image encoder, action sequence as well, action encoder, and then causal diffusion model. So there is cross attention here, I'm guessing. And then output goes back into image and video encoder. This paper will tell us more about video generation in general, which is very interesting to me. I think even though I do more LLMs, I think it will all be unified. LLMs will train on videos, on images and everything. Current video generation models are typically constrained to videos of less than 5 seconds due to limited long video training data and prohibitive computational costs. This is about to change. Existing methods for long context video generation can be broadly categorized into two types: combination of multiple short video segments and autoregressive generation approaches. For example, you can generate frames and then generate frames between those, interpolation frames. But then your video length is kind of predetermined, while autoregressive models, you can generate as long as you want. And then there are combinations like diffusion forcing, cause width, and self-forcing. Those are techniques that combine those two. However, these are confined to text to video and image to video, and not this long-form interactive world model video. This is so interesting. Okay, real-time video generation. This is what Grok and XAI is trying to do. And they are probably training this one on raw bytes. Diverse approaches currently exist to achieve a real-time video generation. The primary methods involve increasing the compression ratio of the variational autoencoder, performing knowledge distillation to reduce the number of sampling steps in diffusion models. So when it does 1,000 steps, you train a smaller network that's gonna predict every second step. So that one uses 500 steps, and then you train smaller and smaller neural network that's gonna predict every second, third, fourth diffusion step. Or combining KV cache with a causal transformer to autoregressively infer the next frame. This one, I wonder how this works. I guess this is still diffusion transformer and just autoregressively predicting the next frame. I'm surprised that all of these methods work. That must say that there is like some universal method that's gonna be even better than every other. Or we are like on a loss curve And we are in all of these kind of same points, but there is like a bottom, the best point that we did not discover, where all of these will converge, all of these models, as we improve them. LTX video achieves generation time shorter than the video duration. So it can generate faster than the video duration. It can generate second of video in less than a second on H100 GPUs by optimizing variational autoencoder compression ratios and applying model distillation techniques. Then we have next frame diffusion, self-forcing cos-vid oasis, leverage the characteristics of autoregressive models combined with knowledge distillation to enable efficient few-step generation. This is also interesting. Although these works achieve a real-time video generation, most of them cannot support real-time interaction. While Oasis manages to enable real-time interaction, its visual quality degrades rapidly during the inference of long videos. In our work, we follow the training paradigm of self-forcing to allow few-step inference, achieving not only fast long video generation, but also maintaining stable and consistent frame quality. Let's go. I already talked about their data pipeline. They just maybe describe it in a bit more detail here. So here is the pipeline for Unreal Engine. They have this navigation mesh, 3D scene, and character controller, and camera controller, auto movement component, and then video recording, and then collecting data into CSV, I guess controller data, and then rendering a video file MP4 and behavior data CSV. Interesting. This is what it looks like. I know Unreal Engine a bit, so this green thing is where this actor can go. It can walk on this, and then that's navigation mesh. So it's made for games to implement NPCs walking around, and they're just using this mechanism. So this is trajectory example. I'm pretty sure Unreal Engine has already ways to make NPCs move around, so you don't even need to code that. They just use single RTX 3090 to generate data. This is gonna get a lot bigger, and there will be a lot more data, and it will then the model will be a lot better. And then they describe GPT-5 data using some script. Here they explain like how they're encoding. So they're using this 3D variational autoencoder and clip image encoder. Diffusion transformer generates a visual token sequence, which is subsequently decoded into the video through 3D VAE decoder. They're using good old rope. Everybody's using rope. It's good for everything. A lot of details on their architecture and some maths. Self-forcing mechanism means during training, the model is generating based on its own previously generated frames, not based on correct frames, ground truth. This is probably smarter than replacing each frame and generating next frame just on the ground truth real video during training, because then model learns that it depends. Its performance depends on how good the frames are. Why this matters? Traditional problem. Most autoregressive models suffer from exposure bias. They are trained on perfect ground truth data, but must use their own potentially imperfect outputs during inference. This causes error to compound over time. Self-forcing solution. By training the model to generate based on its own outputs from the start, it learns to correct its own mistakes, be robust to imperfect inputs, maintain quality over a long sequence. So the base model is this SkyReels V2 image to video 1.3B, a pre-trained video model. Model size 1.3 billion parameters, sweet spot for quality versus speed. So you need to load the checkpoint of this model and remove text modules. We want pure visual understanding. I think this is just mocking code, mock code, example code, not real code. Then for each block in the diffusion transformer blocks, we add action module. This is the interactive controls. It shows here training config steps 100 to 20,000, learning rate, batch size, video length. So I guess it took this from the paper. And then we have distillation. So from teacher to student, fast student, smaller student model. So generate, for example, 40,000 examples from the slow teacher model, and then save the whole trajectory of how those examples were generated and denoising steps. Then they first train student model on the teacher's outputs, but for example, 6,000 steps, but for the last 4,000 steps, it trains on its own outputs. So like the teacher model trained. So using self-forcing. They have these settings: chunk size 3, process 3 frames at a time, attention window 6, look at 6 recent frames, KV cache size 6, remember 6 frames of context, denoising steps 3, only 3 steps to generate versus 50 plus normally for the big model. So 3 for the small student model. Now I think GENIE 3 looks back for more than 6 frames somehow, because you can turn around, walk around, and then turn around back, and there will be same things that was there. And this is the real data. So 153 hours of Minecraft, you can see this outlined here. Unreal Engine 615 hours, real world Sekai 85, GTA 5 driving, and Temple Run 560. All videos are 352 times 640 resolution, 57 frames each video. Then we have some speed boosters, VAE caching, goes from 15 frames to 21 frames, halve action modules from 21 to 23 frames. So use action modules in first half only. I'm not sure what Opus means by this. Reduce denoising steps. You can use 3 instead of 4 denoising steps, and frame rate goes from 23 to 25. So the foundation model, the teacher model, is starting from this Sky Reels, which is pre-trained on a massive video dataset, and it understands motion physics, object permanence, and can already do image to video generation. So this can save months of training time, millions of dollars in compute, terabytes of video data, and they're gonna train just for 2 weeks to adapt this to this base to this teacher model. So in 2 weeks they create teacher model, 8 age 100 GPUs for 2 weeks, distillation 3 days, so the student model, and total 17 days of real-time interactive video training. Sometimes it makes mistakes. This is type of mistakes. It says here oversaturated regions. I'm not sure what it means. Maybe this, what is this black thing here? I don't know. And here, yeah, this is degradation. So further, it needs to improve on auto distribution scenes, for example, moving forward for a long time. This can result in oversaturation or degraded results. And we need to increase resolution. Let's check GitHub repository here. We have this MatrixGame, and then let's go to MatrixGame 2. These images, we already saw them. And let's take a look at one. This is by Quen, I'm not sure. We got modules, let's check modules. Action module, attention. Attention is gonna be the class flash attention here, this is it. Attention, it's cool. Let's go VAE. RMS norm, upsample. Resample, I'm not sure exactly what this is. Residual attention block, encoder 3D, decoder 3D. Okay, we can go to this code, try to code this ourselves in one of my next videos. Maybe we'll see. If we go back to MatrixGame 2 and we say pipeline, causal inference, that's not it. Utils. So everything is just in one, but we got scheduler here for diffusion. So I guess everything is in one. Distributed, okay. Text to video, but in modules, we have action module that they created, I'm guessing. It looks cool. I would clone this and talk to AI, to Claude, to explain this to me. This forward pass is ginormous. From here, all the way down. This is the biggest forward pass I've seen in my life. Maybe we'll code this from scratch. I want to eventually be able to code video models from scratch and merge them with LLMs and do research, which is gonna happen soon, I think. Check out other videos on my channel and see you next time.